Alright, so today we're going to go ahead and talk about the dissociation of weak acids. So whenever we're talking about the dissociation of weak acids, we can use our equilibrium constant, just like we did last unit. So let's look at this general reaction right here. So we have our weak acid, HA, dissociating into H3O plus and A minus. So if we write out our equilibrium expression for this reaction, we have H3O plus times A minus divided by HA. So the way that we denote that it's an acid dissociating is we put the subscript A. So Ka means we're talking about the dissociation equilibrium constant for an acid. So we'll use Ka to judge the strength of an acid, so to what extent this acid dissociates by. So the larger the Ka, that means your numerator is dominating. So there's more hydronium ion present, or there's more conjugate base present. The lower Ka is, that means that we have more of our acid intact. So we have less hydronium and less conjugate base present in solution. So another thing that is sometimes useful is to find the pKa. So pKa is just like pH, so we take the negative log of Ka. And what we'll find here is that as the pKa is increasing, Ka is decreasing. So this can be thought of just like pH. So the pH gets higher, okay, as the hydronium concentration decreases. So that means your hydroxide concentration was getting higher. So here we can look at Ka versus pKa. So a stronger acid will have a lower pKa. So let's go ahead and look at some examples really quick. So here are some common acids, their Ka values and their pKa's. And what we'll see is that strong acids that we assume to dissociate completely, like hydrochloric and nitric acid, they have Ka's that are greater than 1. Their pKa's are negative, so these are really strong acids. Then, if we look at some common weak acids that we'll encounter, so hydrofluoric, acetic, and then the ammonium ion, we'll see that their pKa's have values from 3 to 10. Okay, so the pKa's are useful because this allows us to use that logarithmic scale and use numbers that are a little easier to think about than the Ka's, so 3.5 times 10 to the negative fourth. So we can get an idea of the acid strength without having to think about what the Ka is and what order of magnitude it's measured to. Alright, so let's go ahead and try a few examples using what we know about equilibrium constants to find out some information about pH and then Ka and pKa. Alright, so here this problem is looking at, we're looking at the pH of a 0.25 molar hydrofluoric acid solution is 2.036. And we want to find the values of Ka and pKa for the hydrofluoric acid. So the first thing you want to do is you want to start by writing a balanced chemical equation. And we're going to look at the dissociation of an acid. And we know that we're going to do this because it's asking us to calculate Ka. So we'll have HF plus H2O. I'm going to use the Bronsted-Lowry definition here instead of the Arrhenius definition. And what we'll see is this HF is going to dissociate into the hydronium ion and the fluoride ion. Please disregard the Star Wars noise in the background. There's an epic battle occurring right now. So, if we look at the initial concentration of HF, it's 0.250. We'll assume that there's no initial H3O plus or F minus in our water sample. So then whenever we let these two react, the change will be minus X plus X plus X. Okay, so there's another piece of information that is given in this problem. We're given that the pH is 2.036. So what that means is that's the equilibrium concentration of H3O plus can be calculated. So we know that pH is equal to the negative log of H3O plus So since we're given the pH, we can figure out the concentration of that H3O plus. Taking H3O plus is equal to 10 to the negative 2.036. And we find that this concentration is 0.009204 molar. Okay, so now that we know the concentration of the hydronium ion, that means we know what X is. So X is in fact 0.009204. Okay, to save space, I'm just going to go ahead and write X down here. But we know that we can substitute in the 0.009204 as our X. Alright, so now X is no longer a variable. We know it has a known value. Okay, so we could plug in and actually solve for these equilibrium concentrations. So since we are asked to find Ka, we know that Ka is equal to, well, we take the product, so we have H3O plus times F minus all over HF. And then we can go ahead and plug in our values here. So we know the equilibrium concentration of H3O plus and F minus. We can calculate this here, throw it in for HF. And we can calculate Ka to be 3.52 times 10 to the negative fourth. And then if we're going to look for pKa, pKa is again equal to the negative log of Ka. So plugging that in, we get the pKa to be somewhere around 3.45. Alright, so now the neat thing about this problem is we can go ahead and double check our work because we know what Ka and pKa are for HF. So let's go ahead and check our table. So HF has a Ka value of 3.5 times 10 to the negative fourth, and a pKa value of 3.46. And this is what we found. So we found the Ka to be 3.5 times 10 to the negative fourth, and the pKa to be right around 3.456 or 346. Alright, so these problems are just like the other equilibrium problems that we've done before, but now this time we're looking at a specific type of reaction, the dissociation of an acid. Alright, so what I'd like you to do is go ahead and try this next problem on your own, and then double check your work to make sure that you're getting the same thing that I did. So go ahead and pause it. So as we look at this problem, we approach this the same way we did previously. We write out our dissociation reaction for our weak acid here. Okay, so we have HOCl plus H2O yields H3O plus OCl minus. We know the initial concentration of our weak acid, and we know the concentration of the hydronium ion from the pH. So this allows us to go through and calculate what X is. So we calculate the hydronium concentration, plug it in for X, go through and calculate Ka for the dissociation of this acid, and then also the pKa. So what we're going to do is we're going to go ahead and skip this part here. We are not going to encounter any real situations whenever the Ka is close enough to water that we start to have to worry about the hydronium concentration contributed by the water. Okay, so that means we can skip this one, and then we can go ahead and skip this as well. So more or less what we were going to prove here is that you can ignore the concentration of OH minus and H3O plus pretty much all the time. Alright, so the next problem, I already have the solution here, but I'd like you to go ahead and pause it and try to solve it on your own. This time, different information is given to you. All right, so what we find here is that we're looking at the dissociation of HF again. We're given an initial concentration that we can plug in. We don't have any initial concentration of H3O plus or F minus. In most of the problems like this, you would have a table that gives you Ka, so this would be a given to you on problems like this, because otherwise you wouldn't have enough information to be able to solve for the hydronium concentration. So you'll go ahead and plug into your ice chart. So you'll have 0.050 for your initial concentration. Then you'll have the changes minus x, plus x, plus x. And this time you'll have to use the quadratic equation because you'll set up your expression for Ka right here. And then you'll have hydronium times F minus over HF. We'll substitute in our variables, so we'll have x squared over HF because both hydronium and the fluoride ion are x. So then what we can do is we should solve for x, and we should find that x is 0.0040. So from here we know that the concentration of H3O plus equals the concentration of F minus. So that means the concentration of both of those are 0.0040 molar. The concentration of HF, we can just plug in x here, solve for the concentration of HF. We can find the pH from the concentration of H3O plus right up here, using pH is equal to negative log of H plus. And then finally, since it's also asking about the concentration of OH minus, you could either find the POH and then work backwards. I chose to use KW here. So KW is equal to H3O plus times OH minus, where KW is 1 times 10 to the negative 14th. So we were able to plug in and solve for the concentration of OH minus. So then you can answer any question about the concentration of any species present, or the pH or the POH on a problem like this. So again, this is just like what we've done previously with equilibrium expressions and ice charts, but now we're looking at the specific reaction of weak acid dissociating. The last thing that is another possibility is sometimes you'll see people talk about the percent dissociation in solutions of weak acids. We won't really use this so much. This is more likely to be somewhat of a multiple choice question if you are to encounter this. But what this shows us is that Ka and this percent of dissociation are a way to measure the strength of the acid. So your percent of dissociation would be how much is dissociated divided by the initial concentration. So here, if we assume for our generic reaction, so we'll have acetic acid, and here I'm just going to write out the Arrhenius definition. So we have acetic acid, and then this would dissociate to form H plus our acetate. Okay, so the initial here is 1 molar acetic acid. We'd assume we have 0 H plus, 0 acetate. We set up the change, and then what we would be able to do is plug in this concentration here for our equilibrium concentration. So that means that this is the change. This is the amount that was dissociated. So what we could end up doing is plugging in this here for our initial concentration, the 1 molar. Plug in that because that is the concentration of the dissociated acetic acid. And then because if we measure the equilibrium concentration here, which would be, let's see, so 1 minus 4.2 times 10 to the negative third, we end up getting essentially, let's see, so it's 0.996, and then keeping track of sig figs, we're going to see that this barely dissociates. So there's very little that's dissociated. So this is the concentration of the acetic acid that is still intact. So, but this is just another way that we can measure the strength of an acid. So next time we'll talk about polyprotic acids. We won't encounter these nearly as much, but I'll show you the systematic way that we can go through and find the pH of these polyprotic acids.